Well, it's another day and another test, though it's not a real test. Of course, this is our series convergence test that we're going to learn, but another day, another series convergence test learned. We are going to warm up for this AP Calculus BC lesson with 3 series, and it's your goal to decide which series converge or diverge, and you do need to justify your answers about the convergence or divergence of each series. So go ahead, pause the video, see what you can do, and then we'll come back together. All right, hopefully you've had enough time to look at these. Let's see how I would justify each of these. Well, on A, you could go the long way around and say, oh, this is n to the first power. This is a p series, and the p is less than or equal to 1, which means the series diverges. However, I probably wouldn't go that route. Instead, I would look at this and say, oh, hey, this is the harmonic series. And so I would say this is the harmonic series. Spelling is crushing it today. Therefore, the series diverges. And that's all you need. Once you've identified the type of series, it's a harmonic series, you can say the series diverges. You could have used a p-test there. That's probably the fastest way, though. So let's go ahead and look at the other two. 1 over n factorial and 1 over n to the n. Well, looking at these, I'm pretty confident that both of these are going to converge, but I'm not quite sure why. Now, I mean, if you picture this right here, right? I mean, think about the denominators. 1 to the first, and then we have 2 to the second, and 3 to the third. Look at all these exponents. Almost every exponent in here is going to be a p-value greater than 1, except for this first one, but we know that one term doesn't throw off convergence or divergence. So since in the sequence every exponent is larger than 1, my guess is you could probably relate it to a p-series and say, well, this is definitely going to converge. And you're right, these fractions become very, very small very quickly, and it will converge. On 1 over n factorial, if we look at these, we get 1 over 1, right? And then 1 over 2 factorial, and then 1 over 3 factorial, and then 1 over 4, and of course, so on and so forth. But the whole point of this is realize that eventually each of these is going to have a power bigger than 2. Imagine if you're doing 2 times a number. Well, 2 times 2 is 2 squared, and that'd be a p-series. Even 3 times 3, and I know this is 4, but 3 times 3 is a p-series with p greater than 2. And we're doing 3 times 4. That's even bigger than 3. So my point here is that I think the denominator is going to get really large really quickly, but we're still not quite sure how to justify. So my guess is that both of these converge. I'm just not quite sure why. Now, what we're going to deal with today then is the ratio test. And the ratio test is really, really good at dealing with factorials and powers. And in fact, I would say the ratio test is probably the most common test we're going to use this semester. It's fairly wide-reaching, meaning you can use it on lots and lots and lots of series. And it rarely is inconclusive. It will be inconclusive at times, but it's not the integral test where you have to go through the whole process of doing an integral and concluding. P-series, of course, if you get a p-series, then just use the p-series test. But pretty much everything else, you usually can use the ratio test. It's not always the most useful, and we'll talk about some others that are, but it's the one we will come back to the most. So we're going to start by defining R as the ratio between 2 consecutive terms. Now, we've actually looked at types of series before that use R for a ratio. In particular, we've looked at geometric series. And we also know that from geometric series, we take the next term and divide it by the current term, right? If you had the series, we'll do an easy one. We'll go 3, 9, 27, 81, so on and so forth. If you take a current term and divide it by the previous term, then you will always get that common ratio. It's being multiplied by 3 every time. Now, it actually turns out, and this is a pretty wild fact here, that any series which converges and for which the ratio test is valid, and we'll look at ones that it's valid for, has terms, once you go out infinitely far, which behave like a geometric series. So that means eventually when our pattern gets large enough, there's going to be a common ratio. Even if there originally wasn't a common ratio, there will be eventually. And if you want a cool proof of that, page 644 in your book tells a little bit more. So why is that useful? Well, if eventually, and all infinite series go to infinity, if eventually this infinite series has a common ratio, then we should be able to examine that common ratio and look at it and see, oh wait, is this going to cause our series to converge or diverge? Because we need to remember that in order for a series to converge, the absolute value of the ratio has to be less than 1. So therefore, if we evaluate the limit of the ratio of two consecutive infinitely large terms, and we find the answer to this ratio up here is less than 1, then our series converges. We're basically looking at two super infinitely large, though small terms, and finding the answer. Now, we can summarize this too. So if you're given a series here, what we're going to do is we're going to find the limit as n goes infinitely large. We want to look at the end of the series of our ratio. And our ratio is created by doing a sub n. This plus 1 is supposed to be down here. It's supposed to be a sub n plus 1. And I think I mess that up every single time. That's awkward. A sub n plus 1 divided by a sub n. And when we finish evaluating this, if our answer is less than 1, then we have a convergent series. If we have an answer that's greater than 1, it's divergent. We are not sure about its convergence if it equals exactly 1. Okay. Now, of course, knowing what the ratio test is and actually using it are two different things. So let's go ahead and practice a couple ratio test problems. I have 3 problems on here. Again, really crushing my lettering here. This should be B and C down here. But I tried to pick 3 problems that I thought are pretty different from each other. Okay. So let's look at our first one. The nth term here, and you probably won't write this in the future, but I think it helps to look at in the beginning. The nth term is just like the general term. The nth term is 10 to the n divided by n factorial. We also need the n plus first term. Okay, and that term is 1 bigger than the nth term. So how do we show 1 bigger? Well, we say this becomes n plus 1, and this becomes n plus 1. Now, the ratio test tells us, and I always like to set this up to have 2 sides so we remember what we're doing. The ratio test tells us that when we take the limit, I should work way over here. This is going to be tough. That's okay. When we take the limit as n goes infinitely large of my n plus first term to the nth term. We do want to keep that order. We want to do the further one divided by the less far one. And it needs to be the absolute value because this is like my ratio, right? As long as this ratio is less than 1, then our series converges. So let's plug a few things in. We have the limit as n approaches infinity. I'm going to do this. I'll probably need a second side over here of, well, what is a sub n plus 1? Well, that was my n plus first term. So that's 10 to the n plus 1 divided by n plus 1 factorial, divided by my nth term. My nth term, my general term, is 10 to the nth divided, zoom in a bit, sorry, divided by n factorial. And that has to be less than 1. Of course, you're probably looking at this monstrosity going, why, how, what? Are we going to be able to simplify this? Well, yes, we are. So let's start right now. The first thing we're almost always going to do when we simplify is we're going to multiply by the reciprocal of this denominator. So when you multiply by the reciprocal, right, so n factorial over 10 to the n, that of course will cancel everything out here. But to keep a fraction equal, whatever you multiply the denominator by, you need to multiply the numerator by that as well. So we end up getting, and that absolute value is pretty important, we end up getting this 10 to the n plus 1 divided by n plus 1 factorial times n factorial divided by 10 to the n. And this whole thing still needs to be less than 1. All right, well, now that we're here, we can start simplifying. And full disclosure, you're going to start doing this really quickly. You're going to see this, you're going to flip the second fraction, and you're going to go straight there. That's awesome. I wouldn't show what I did in blue there, but it's always good for the first time through. So we're going to have to simplify this down as far as we can, because right now plugging in infinity just isn't going to go well. We want to clean this up, and usually you can clean these up quite well. So what we're going to do is look at the limit as n approaches infinity. And then we have 10 to the n plus 1. We'll split that. 10 to the n times 10 to the first. Divided by n plus 1 factorial. Well, don't forget that n plus 1 factorial is n plus 1 times n minus 1 times n minus 2. Wait, isn't this whole thing right here, isn't that just n factorial? N times 1 smaller times 1 smaller it is. So n plus 1 factorial can be split as n plus 1 times n factorial. We've seen that before. Times n factorial over 10 to the n, and all of that still has to be less than 1. Okay, well, can we clean this up? I think we can. We have the n factorials, those are gone. The 10 to the n's, those are gone. And then, although it might seem weird now, if I ever have a constant, I always like to factor out the constant from the limit. So this constant is 10. The absolute value of 10 isn't going to change. I'm going to take that 10 and move it out front. And then we're going to find the limit as n approaches infinity. Well, nothing is left because I pulled this 10 out front. So of 1 over n plus 1, which is less than 1. So get in the habit of factoring out that constant. Or if the constant was negative, make it positive, then factor it out. Because now this becomes much easier. When we substitute in infinity, we have 1 over infinity, which is, of course, 0. 10 times 0, that's 0. 0 is less than 1. Therefore, we can jump back to our series, and we could say something like, by the ratio test, the limit as n approaches infinity of a sub n plus 1 divided by a sub n is less than 1. Therefore, the series converges. So, although there is a bit of work here, I really just get a nice sense of satisfaction when everything cancels out. And you're going to find that almost everything does cancel out using the ratio test. And you can go much quicker, too. Nothing too bad. You just need to ensure that your final answer is less than 1. So let's try 2 more. In fact, you might even want to pause this video and try 2 more on your own. They're really not too bad. And then you can play this forward at 2 times speed and see if you did it right. We already know the answer to this next one. This is a harmonic series. We know it diverges, but let's see what happens if we try something in our ratio test that we already know diverges. So again, our nth term is going to be 1 over n. That's the general term. The n plus first term is going to be 1 over n plus 1. So when we tackle this ratio test, and I'll show you a different way to do it, sometimes people will just work from left to right. We're going to do the n plus first term divided by, that doesn't look like an absolute value, there we go, divided by this. Okay. You're going to multiply by your reciprocal, so that gives you 1 over n plus 1 times n over 1, which, and I'm just working to the right now. We get n divided by n plus 1. A lot of people I find start here and just instantly skip here. They skip that middle step, which is fine, right? We're trying to be efficient here. And then this is a limit we can take. In fact, it's all about dominance, isn't it? It's the limit as n approaches infinity, n divided by n, which I think gives us 1. So for this ratio test, right, so we'd say as the limit as n approaches infinity of a sub n plus 1 divided by a sub n equals 1, then we say the ratio test is inconclusive. So if the problem had asked you to prove if this was or draw a conclusion using the ratio test based on this previous page, since we got exactly 1, we don't know anything about the convergence. Of course, I never would have used the ratio test in the first place here because this is the harmonic series, and we know the harmonic series diverges. But if you do get 1, you do have to say that it's inconclusive. Okay, let's jump down to our last one. I'm not going to work with that series. I'm definitely going to get rid of our negative exponent and treat this as n squared plus 4 divided by e to the n. let's go ahead and work this through. So we have the limit as n approaches infinity, and we're going to just kind of skip to right to our n plus first term. So we have n plus 1 squared plus 4 divided by e to the n plus 1. That's the n plus first term, divided by n squared plus 4 divided by e to the n. We're going to need some room here. There's a bit of cleaning up we'll need to do, I think. The limit as n approaches infinity of, then we have n plus 1 squared plus 4 divided by e to the n plus 1 times the reciprocal, so e to the n divided by n squared plus 4. So really what this is doing is it's basically saying what will cancel out for each of the corresponding terms out at infinity, and it turns out quite a bit. So we're going to go equals the limit as n approaches infinity. We're going to probably have to multiply all this out. You might not have to, but it's not a bad idea. So we get n squared plus 2n plus 1 plus 4 divided by e to the n times e to the first times e to the n over n squared plus 4. Okay, well, the e to the n certainly cancel. And notice that e is a constant that's multiplying. So I'm actually going to factor out that e, or 1 over e, it's in the denominator, and see what that leaves us inside. Again, the more constants you can factor out of your limit, the happier and the easier this is going to be to figure out. So n squared plus 2n plus 5, 4 plus 1, right, over n squared plus 4. Well, we do actually need to evaluate this limit here. So the limit as n approaches infinity, think dominance, my most dominant terms, n squared over n squared, which is of course 1. So 1 over e times 1, which is just 1 over e. All right, well, what can we conclude by this? Well, I always like to finish and say, is this less than 1? Well, e is 2.718, 1 over 2 and 1 over 3, somewhere in between 1/2 and 1/3, and that's definitely less than 1. So yes, that's totally true. So then we'd say as the limit as n approaches infinity of a sub n plus 1 divided by a sub n is less than 1, then the ratio test shows the series converges. So nothing too terrible there. Now, please remember that we are learning these different tests to expand our list of series for which we can identify convergence, right? The main function that the ratio test helps us with is actually well, I even gave you this clever pun at the end. It's actually the factorial function. It gives us a really nice way to determine if things with factorials converge or diverge. And we end up using at the end of the semester factorials all the time. So you'll find that you really rely on the ratio test over every other test. That doesn't mean we won't use other tests, but we definitely need to be pretty confident with this ratio test. So in fact, we've actually learned 6 tests and or series so far. So I'd like you to just take a couple minutes and see if you know what each of these are. So either giving a definition of each one, how to use them, what you need to state, so on and so forth. And then once you've tried that, and there's a bunch of space on here for you to organize it, give examples, unpause and see how you did. Okay. Well, there are 2 series on here that we can actually find the sum for. We know how to find the sum of our geometric series and our telescoping series, right? Geometric is always going to be, and there should be a sigma in front of each of these, I just don't want to draw it, should look something like this, and we know that in order to find a sum, our ratio has to be less than 1. Telescoping series are a little bit harder to pin down, but usually it's something like 1 over k minus 1 plus 1 over k, something like that, where you have 2 terms that are pretty close together and there shouldn't be a plus in there. There's going to be a minus, and things are going to start to cancel out when you start to write out all those terms. But those are really the only 2 that we can find sums for. Now, the other 4 are really tests to determine if something converges or not, and we always need to start with the main divergence test. That's the first thing we always start, and that's where we take the limit as n approaches infinity of just the sequence. And we really need to make sure that equals 0. If it equals 0, then our series has a chance to converge, right? So we would say may converge. However, if the limit as n approaches infinity of a sub n is not equal to 0, so any other number or infinity or does not exist, then it's an automatically diverge and you get to stop. So you might even cross your fingers and go, I hope this diverges, or I hope we get not 0 because then we can stop, because you're right. So then we've learned 3 other tests on top of these. In order of each of them, the integral test is my least favorite because it's the most work, right? The integral test says instead of looking at the sum, let's say from like 1 to infinity of a sub n, we instead would take the integral from 1 to infinity of f of n, and we'd say, okay, does that integral actually equal something, right? And if it equals a number, then both of them converge. However, if your integral equals, let's say your integral diverges, right? We don't get an answer, then it means that both the series and the integral diverge. Bunch of work there, though. You can also use the integral test to bound the sum. You can say, well, I don't know the exact sum, but I'm pretty darn confident it is between these two. That's a good way to go. The next piece that we learned was yesterday, no, 2 days ago, because we had our practice quiz, and that was our P-series test. The P-series test is a real easy, straightforward one. You should hope, and these do actually pop up, usually 1 per year on the multiple choice. We're just looking for 1 over n to the p power, and we know that if our power is less than or equal to 1, then that series will diverge, right? Harmonic or smaller. However, if p is greater than 1, then we know that our series converges. And then the last one, of course, is the ratio test that we just learned today. And we want to make sure that the ratio is less than 1. And to find the ratio of any series, we just look infinitely far out to that series, and we take the a sub n plus first term, divide it by the a sub nth, and make sure it's less than 1. And if it is, then we know that our series converges. Equal to 1, inconclusive, less or greater than 1, divergent. Okay? So I think that's a nice summary of all of our tests. You will get a nice little cheat sheet at the end, but it's not a bad idea to put these on note cards. There are a lot of tests that are thrown at you. We're only about halfway done with them so far. So make sure that you are comfortable with these, and at this point, you can go ahead and start your bookwork. Good luck. Thanks for being wonderful, and I'm excited to see you next class.